Okay, welcome back. This is Calc 1. We are prepping for test 2, and this is a sample of questions I may ask. Okay, or at least they should be modeled on something like this. So the first one, we have two cars leaving the same location at the same time. The first car heads north, 20 miles per hour. The second car is heading east at 30 miles per hour. How quickly is the distance between them changing 30 minutes after they leave? All right, so let's go ahead and draw us a little picture here. Okay, so we have, oh, do with this, put that. Okay, so here we go. We have two cars leaving same place at the same time. One is leaving due north at 20 miles per hour. We're going to call this one Y. The second one is leaving 30 miles per hour to the east, 30 miles per hour. We're going to call this one X. Okay, so right away we have some stuff we could write down. We could say dy by dt is equal to 20. We could say dx by dt is equal to 30. Okay, so if we want how fast is this distance? This distance here, actually I'm not going to call it d, I'm going to call it r. How fast is this distance here increasing? Okay, so that's what we're trying to figure out. Well, if I didn't know better, I'd say this was the right triangle. So what we're going to say is that we have r is equal to x squared plus y squared raised to the 1/2 power. Okay, and now we have to figure out, we take the derivative of both sides here. So we're going to say dr by dt, that's how fast is the distance increasing, is equal to 1/2. And then we have x squared plus y squared to the negative 1/2 power. Then we need a chain rule. We need a 2x dx by dt here plus a 2y dy by dt here. dy by dt here. Okay, and that's what's going to happen. There's a little bit of algebra we could do. We can get rid of the 2's because that's going to cancel with the 1/2. And we have dr by dt is equal to, let's go with something like x times dx, or no, what did I do first? Just to keep it consistent with my notes. So I did the north one first, not a big deal. But we have y dy by dt plus x dx by dt. So fortunately, arithmetic is commutative, so we can just swap the order, it's no big deal. And on the bottom here, we have the square root of x squared plus y squared. Okay, and then we have to figure out what x and y are. Okay, it's been 30 minutes. They gave us problems in miles per hour. So our time is equal to 1/2 of an hour. Fair for me to say that 30 minutes equals 1/2 an hour. So my y value, 20 times 1/2 is equal to 10 miles. My x value, 30 times 1/2 is equal to 15 miles. All right, and that's all we're going to do. We're just going to plug this stuff in and we're going to see how we go. All right, so we have effectively the calculus part is over. Now it's just arithmetic. Okay, so we have dr by dt is equal to 10. How fast is this car traveling? By 20 plus 15. How fast is this car traveling? By 30 divided by, and all we have down on the bottom here is the square root of 10 squared plus 15 squared. Okay, now it's just a calculator exercise. Okay, on the top I got 650. On the bottom I got the square root of 325. Okay, we're going to be a little bit nicer about that. We're going to say, hey, 650 is 13 times 10. 325 happens to be 25 times 13. Okay. So we can do some algebra trickery here and deal with dr by dt is equal to 10 times 13 over the square root of 25 is 5, and then we still have the square root of 15 under here. So this is just going to be 10 over 5 is 2, and then we have 13 over root 13, which is going to be, the root 13s are going to cancel, and I'm just going to have 2 root 13, and that seems like about it. Yeah. So that is how we do that. You can go ahead and plug this into your calculators and get an answer, but this is a very good answer. Okay, so how about we look at the next one? Boyle's law states, so what you should be reading into this is there's two related rates problems on your pretest. Chances are there's going to be two related rates problems on your actual test. I did pick the hardest possible ones I could find. Okay, so if you're thinking about having to construct a whole bunch of geometry and deal with that kind of construction, I could do that. You might want to practice one or two of them just to be safe, but at the end, I kind of have to ask myself, what am I grading? And the point of this is to grade your knowledge about how to do a related rates problem. So it can't be that complicated geometrically, okay, not to do this. One of them can be, but there's going to be one hard one, one easy one. Okay, and hard is relative to what I think is hard, relative to what I think is easy. So, but chances are there's going to be two different levels of them. One might be a little bit easier than the other, but there we go with our Boyle's law, and then dealing with that. Okay. So here we have Boyle's law states that when a sample of gas is present, you have PV is equal to C, and in a given instant, we want the volume to be 500 centimeters cubed, and pressure is 100 kilopascals. I am not trying to trick you with units. Okay, you've seen how tricky I can get, and that is miles per hour, and then talking about 30 minutes. Okay, that's as tricky as it gets. So if we're looking for centimeters cubes versus kilopascals, the units are supposed to work out. They are not supposed to be the tricky part of the problem. Okay, suppose the pressure is increasing at a rate of 40 kilopascals. At what rate is the volume decreasing in this instant? That makes sense, right? If this has to be constant, if the pressure is going up, the volume is going to go down. Okay, so we have PV equals C. Okay, and then we have to get a related rate here. So what we're going to do is take derivatives of both sides here. So this is a product rule because both of these are functions of time. So derivative of the first is dp by dt times v plus the first p times the derivative of the second, dv by dt. And fortunately, the derivative of constants are 0. So there we go. Okay, and what did they actually want to ask? They wanted to know at what rate is the volume decreasing. So we're going to be solving for our volume here. Okay. So we're just going to go ahead and send the other one to the other side. So we're going to have P times dV by dt equals negative V dP by dt. Okay, so dV by dt is equal to negative V over P times dP by dt. And now it's just time to plug some stuff in. Okay, so that's not so bad. So dV by dt, we're just going to say, what do we have here? We have volume was 500, negative 500. The negative sign will take care of the decreasing. We don't have to worry about that. Okay, the pressure is 100. And then, let's see here. Did they say how the pressure is increasing by 40? So a bunch of stuff cancels, and we get negative 5 times 40. So dv by dt is equal to negative 5 times 40, which is negative 200. Okay, and it's going to be in cubic centimeters. Okay, so that is pretty much how you do that kind of a problem. So again, practice some related rates problems. Don't go too crazy with the geometry of them, but you should definitely practice. Cones are always a good thing to deal with. Melting snow cones or melting ice cream cones, melting ice cubes, melting snowballs, all of that kind of stuff is all good. Okay, so there's a lot of different. The distance formula one is fine. That's a good one too. So there's a lot of good related rates problems. I think to the one class below you guys, to the applications of calculus class, there's an oil spill problem. I must always ask the business people what the oil spill problem is, because you guys are young. You guys are young enough that you probably don't remember the Deepwater Horizons from British Petroleum, but I do. And they were talking about how fast that oil slick was spreading. And I'm like, no, it's minimal. No, it isn't. I've done this problem. I know that this is not a minimal thing. So that's always my favorite one to give out for the business calculus people. That might be a little bit too easy for you guys, but I have asked that question on this exam for a related class before. So you might want to look at the oil slick problem just in case. Okay. All right. But these are good ones too. So let's say I would definitely ask that one. And then your project had gravel falling on a cone and making a pile of it. You guys did a pretty good job with that project. So that would also be a really good candidate, is a conveyor belt dropping gravel on a conical pile. Okay, that's also a really good problem to take a look at. So those are 4 good related rates problems without going too crazy into designing trapezoidal troughs and filling out how much is filling up, that kind of thing. So again, the important thing is I need to grade you on related rates, not setting up a problem. Those are good homework problems. They are not good test problems. Okay, so let's see what we have next. We have the edge of a cube was found to be 15 centimeters with a possible error of 0.1 centimeters. Use differentials to estimate the maximum possible error. Find the percentage error when computing, and find the relative error and percentage error when computing both the volume of the cube and the surface area of the cube. These can be pretty long. I only put one example up here for this thing, and that's pretty much what I want to do. I may not ask the A and the B for this guide, but be prepared for it just in case. Okay, let's deal with the volume. We are given that the side is equal to 15 centimeters. We are given that, actually, let me change my S's. Okay, I always use a script S because my other S's look like 5s, whereas that doesn't look like anything. Delta S is 0.1. Okay, so we have that. Okay, so we have volume equals S cubed. And they want to use differentials to estimate the error. Okay, so we have dV is equal to 3s squared times change in S. Okay, so if I just wanted the maximum error, what I would do here is I would say, okay, well, dV is equal to, and I would start plugging some things in. So we would say dV is equal to, delta V, I should say, not D, I should use delta V, because we're using differentials, not derivatives. So delta V is equal to, and I've got 3 times 15 squared, okay, times 0.1. Put that in the calculator, and I get delta V is equal to plus or minus, and what do we end up with here? 67.5 centimeters cubed as an error. This might be one of the few formulas you actually use on the job if you become some kind of an engineer that is responsible for testing and tracking down error propagation. Like, this is the thing that people actually do. Okay, so this might be a really important section in your book that you might actually use someday after you have finished school. Okay, so we have that. Relative error, which also explains why I still don't know how to do it. Okay, all we do is divide by the v. We're just going to take v over v, which is equal to, right, 3s squared times delta s. What was s? What was v rather? V was s cubed. Right? The v is s cubed. And then we have some simplifying to deal with here. So we're going to have, this is 3 over s times delta s. So my relative error, which is delta v over v, okay, this is just going to be 3 over 15 times 0.1 times 0.1, that way. Okay, and then you plug those into the calculator, and I ended up with a delta v over v was equal to 0.02. Percentage-wise, all we do is move the decimal place over, so percent error here is we just convert it to a decimal, and we just say this is 2% error. Okay, we just move the decimal place over twice. Okay, so that's how you deal with a percent error. Okay. How about for surface area? Okay, surface area is equal to 6s squared. Okay, so we're going to go with our delta SA. This is equal to 12s times delta s. Okay, and again, if I just want the maximum area, we're just going to say this is 12 times 15 times 0.1, 0.1 is what I want to say. Okay, 0.1 there. We plug that in the calculator. Okay, and I got 18 centimeters squared as to my possible error in the surface area. All right, to get the relative error, we're going to say this is delta SA divided by SA, which is going to be 12s times delta s divided by 6s squared, because that was the that was the surface area. 12 over 6 is equal to 2. We have delta s over s, which is 2 times 0.0 or times 0.1. Why do I keep doing this? Okay, 2 times 0.1 over 15. When I did this, I came out with 0.013 repeating. And again, when I want to go into percent error, we just move the decimal place over by 2. So that's going to be 1.3 repeating percent error. All right, so those are pretty straightforward problems, which is kind of nice, but they actually are really worthwhile to learn how to do, because later in life, when you become, you probably get your first job as an intern, as an engineer, you're going to be responsible for requirements docs and making sure that the error is within specifications of what your customer said they want their error to be in specifications of. This is how you tell. Okay, so it's a good thing to know. Right? Let's see here. Oh, that's 4 through 6. We are good. Okay, so I'll go ahead and call it here and wish you the best of luck studying for exam. Don't restrict yourself to just these problems. Practice some of the other ones, especially when it comes to related rates. There's a few of them, but I didn't go nuts and try to find the hardest problem I could find. Okay, I kept them relatively straightforward. Okay, good luck with studying, and I wish you all well.